In this lesson, let's first start by reviewing the basic chemistry associated with alcohols and halogenic acids. And what I have drawn out here are the intermediates associated with the mechanism of the reaction of hydrobromic acid with a tertiary alcohol. So here's my tertiary alcohol right here. And in the first step, and I didn't show the mechanism, I'm just focusing on the intermediates. The first step involves the protonation of the alcohol, then the dissociation of water as a leaving group to form a carbocation, and finally capture of the carbocation electrophile by a bromide ion nucleophile. And these are the standard steps that you expect in a typical SN1 reaction. And from hopefully your memorization of the DUI table by this point, you should have recognized that a tertiary alcohol reacted with HBr will go via an SN1 reaction. And I have these drawn in equilibrium right here to illustrate the next point. But we can actually reverse this reaction. If you'll notice, in this second step right here, which ends up being the rate determining step, a water molecule pops off, which means that as the reaction progresses, water starts to build up in the chemical reaction. And when your chemical reaction starts to build up one of its products, that will eventually start leading to the reverse reaction. So rather than eventually start leading to the reverse reaction, let's just put water in there in the first step. So I'm just going to flip my perspective on this one. And so now, instead of starting off with an alcohol, let's pretend that we start this reaction with a tertiary alkyl halide. In fact, this is probably one of the more useful laboratories that we typically have students do during the first semester of organic chemistry, is a reaction involving the addition of water to tert-butyl chloride is what we use in the laboratory. But tert-butyl bromide works just as well. And we can show mechanistically what happens in this. This is the reverse of the reaction that we saw in the previous chapter. And if you remember, this particular reaction is going to be called a solvolysis reaction. And one of the key steps is the loss of the bromide, and then a water is going to come in here as a nucleophile. Now the first step in this reverse reaction, in this solvolysis reaction, ends up being your rate determining step, because you're forming a carbocation across this first step right here. So this is the RDS. And if we want to kind of track what the energy diagram for that looks like, we start off with some inherent energy level. It goes over some activation barrier, and then it drops out at a carbocation intermediate. After you add the water in the next step, you quench the carbocation, it's going to drop down, and then there's a final step where you deprotonate that alkyl oxonium ion to get to your final spot. So here's just kind of a tracing of the energy. I've tried to coordinate these transition arrows right here, showing going from one step to another with the humps, because that's where the transition state occurs. Let's finish up this mechanism. So in the first step, this rate determining step, you lose the bromide to form the carbocation. That's the largest kind of climb that you have to make, and you end up at that carbocation intermediate. Then in the second step, water catches that carbocation. This is going to be very fast, and it's going to drop way down in energy. And then in the third step, the third and final step, because there's only 1, 2, 3 steps, something needs to come along and pluck that hydrogen off. Now, the assumption of this solvolysis reaction is that we have flooded the system with water. So there is water everywhere. And one of the things you'll find out about water is if water is present somewhere in your reaction, then water does most of the chemistry. Another potential base that you could use to pull this hydrogen off in this third and final step is the bromide ion itself. The bromide ion, when it pops off, can also act and pull that hydrogen off. But it's a weak base, and there's just never going to be that much of it because you only generate one bromide ion per reaction. And if water's your solvent, then water's going to be everywhere. So this right here represents the reverse of the DUI table, where we started off with a tertiary alcohol and turn it into an alkyl bromide. Here we're starting off with an alkyl bromide and turning it into a tertiary alcohol. This solvolysis reaction is mechanistically, well, it's close enough. Let's just say it's identical. that the mechanism that you expect in a solvolysis reaction using water, so specifically a hydrolysis reaction, will exactly match up with the mechanism that you would have expected going from the alcohol to the alkyl halide. So if you expect an SN1 mechanism going this direction, then this solvolysis reaction using water or hydrolysis will follow the same mechanism going back in the reverse direction. So in question part C of one of the numbers on this lesson, I wanted to add in a new table just to put it somewhere, because this is going to be important to us. In the previous chapter, we focused primarily on the alcohol table, the DUI table, I called it. Perhaps not the best name for it, but it is what it is. In this chapter, we're going to start to build a larger table, and that table is going to involve alkyl halides. So this is a common abbreviation for alkyl halides, and as I mentioned previously, alkyl tosylates are just big alkyl halides. So for the sake of memorizing as little as possible, if we just lump alkyl halides and alkyl tosylates together, then everything that we're about to learn about the alkyl halides can also be applied to the alkyl tosylates. And then here, this is the solvolysis, and all I really did was just steal the same symbols, SN1 with a possible shift, and SN2 from the DUI table. Only on the DUI table, we talked about these being alcohols, and this typically involved hydrobromic acid. Here, these are going to be a variety of different alkyl halides, and during the solvolysis reaction, we expect these mechanisms. So the example that I just showed you was the solvolysis of a tertiary alkyl halide, and because, so it goes SN1. That's what the table here is trying to communicate to us. We're going to see some examples of other types of these solvolysis reactions today. And so I just kind of want to dump this table right here in the middle of this lesson plan so that you have it somewhere when you're preparing to study. So we can go ahead and put in a definition of solvolysis here. We used one before, and we had solvolysis show up in the previous lesson. We want to make sure that we capture a definition of solvolysis here again. And so solvolysis is typically, and there's some other reasons, other places we'll see solvolysis, but for now it's typically the conversion, conversion of an alkyl halide or an alkyl tosylate. Remember, we're just kind of lumping those together in terms of their chemical reactivity into an alcohol, and that would be with hydrolysis, or an ether, and that's if we do methanolysis or ethanolysis. So this is hopefully not new information to you. And I used these types of methanolysis and ethanolysis type of reactions in the last lesson. What we're adding here is that the mechanism typically mimics the observed mechanism for the reverse reaction in the DUI table. Okay, so let's apply that statement to this problem right here. So the first thing we're going to look at is the hydrolysis reaction of 2-bromo-3-methylbutane with a 50-50 mixture of water and isopropyl alcohol. And we're going to come back and talk about what this isopropyl alcohol is doing in there. But this essentially is the hydrolysis of 2-bromo-3-methylbutane with water. So this is going to be a solvolysis reaction. Solvolysis is a large generic term. Hydrolysis is a specific term when the solvent is water. So first I want to draw the chemical structure of 2-bromo-3-methylbutane. This is a secondary alkyl halide. And the DUI table tells us that if you take a secondary alcohol and react it with hydrobromic acid, you expect the mechanism to be SN1, but you also have to look out for shifts. And a solvolysis follows the same mechanism as we observed on the reverse reaction. So if a secondary alcohol goes through an SN1 with a shift, then a secondary alkyl halide will also go SN1 and has the potential for a shift. That's what we see in the second step. So the first step right here in the solvolysis is that the bromide leaves to form a carbocation. Whenever you have a secondary carbocation, you have to check both neighboring positions. Over here on the left is a primary position, so we definitely don't want to put the carbocation there. But on the right-hand side, if I slide this hydride over, then I can move the carbocation to the tertiary position. So this is the pathway that we expect to occur. Whenever you can move a hydride or a methyl group, and in that process convert a secondary carbocation to a tertiary carbocation, you expect that to occur. Notice the hydride shift mechanism. From a detail perspective, the arrow is actually coming off of the bond, not the hydrogen, because I'm not moving the hydrogen necessarily. I am moving the hydrogen's electrons. So I'm pulling this bond, and the hydrogen just happens to follow those electrons across. So if you've drawn these arrows before, make sure that when you're doing these hydride or methyl group shifts, that you're shifting from the bond and not from the atom out here on the end. Okay, so this first step is the rate determining step. It's where we form the carbocation. Then in the second step, and this happens very quickly, the hydride slides over to produce a better carbocation intermediate. And then finally water, which is the solvent, so it's everywhere, will capture that carbocation. We have to deprotonate that water to get to the alcohol. And again, like the last example I showed you, a bromide ion could also act as the base in this 1, 2, 3, fourth step. In this fourth step, the bromide ion could also come over here and pull the hydrogen off. But when water is present anywhere in your solution, you typically expect water to do all the chemistry. And you might ask the question, well, does it ever happen that it doesn't hydride shift? And the answer is absolutely. That's why in organic chemistry, we have to carefully differentiate between major and minor products. This is the major product that we expect. But an absolutely reasonable minor product would be the water capturing this secondary carbocation before the hydride has a chance to slide over. As soon as that carbocation is formed, it's a foot race to see who can get there first. The hydride shift, the bromide comes back on again and just takes us back to our starting material, or a water can come over and capture the carbocation. All three of those things are attempting to happen simultaneously. The bromide capturing it is the most probable event, but it doesn't actually get us anywhere. It just falls off again. And then the hydride is the second most likely event, and that's the pathway that I've shown you here in this mechanism. If you wanted to show the pathway for the minor product of the water capturing that carbocation, then you just kind of skip out on this step, bring the water directly into the carbocation, deprotonate it with another water, and you end up with an SN1 mechanism with no shift. That will happen, but it's not what we expect to be the major product. And your job is to be able to predict the major product. The chemist needs to know what's happening most of the time, and then also what's happening some of the time, but to focus on what's happening most of the time. I had the fan on in the previous clips, the video clips, so hopefully you can hear a little better now. Let's ask now what the role of isopropyl alcohol is, and IPA is a common abbreviation for isopropyl alcohol. And so you kind of need to recognize that when you see it if you're going to play the game of organic chemistry. One of the problems, and you might have thought about this is a solvolysis reaction, and that means we're mixing this alkyl halide in water as a solvent. But from the solubility rules that we learned in the last chapter, alkyl bromides, in fact, all alkyl halides are never soluble in water. So how can we solvate an alkyl halide in water if it's not soluble in water? And the answer is we use small chain alcohols. So alkyl bromides are not miscible with water, but water and alkyl bromides are both miscible with small carbons. And so if you put IPA in there, it will dissolve in both the water and it will also dissolve in the alkyl bromide. And would the isopropyl alcohol also occasionally stick to that carbocation? And the answer is yes, it just represents another minor pathway. And so again, when we do this experiment in laboratory, this is a very similar chemical reaction that we have students do in the laboratory. The first thing they have to do is mix up the water and the isopropyl alcohol to produce a combined solvent system. That's a very common solvent system for organic chemists to use. You'll just see sometimes just a mixture of water / alcohol is all they'll specify as the solvent. And it's because the alcohol doesn't really matter which one you use. You could use methanol, ethanol, isopropanol. But as the chain starts to get longer, then you run into some solubility issues. So isopropyl alcohol with 3 carbons is about the biggest carbon chain alcohol that I typically see when they mix water and alcohol together as a combined solvent system. All right, so now let's draw an energy diagram for this reaction. There are 1, 2, 3, 4 steps. And so here's the energy diagram right here. R refers to the reactants, the starting materials. The first thing that we did was pop that bromide off, and that makes a carbocation intermediate. So that's the rate determining step, is the initial formation of that carbocation. That was a secondary carbocation. If the hydride shift occurs, then we can drop that down to a tertiary carbocation. And that is fast because the barrier is small and it's not actually that much of a drop in energy. And you're still a carbocation. Everybody's still upset about that. So both of these are high in energy. But the secondary carbocation is worse than the tertiary carbocation. And then something happens to that carbocation to stop it from being so unstable. That's when the water jumps on it. So step 1 is the formation of the secondary carbocation. Step 2 is the hydride shift to move to a tertiary carbocation. Step 3 is water capturing that carbocation. And then finally in step 4 is just acid-base chemistry. And that's why this last step 4 has both a small activation barrier and drops this just a little bit more lower energy in products. And the rate determining step is the one we care about the most. It's where the carbocation initially forms. It's nice sometimes to kind of get excited about where you get all your energy back, but you know you're going to get it back somewhere or the reaction won't work at all. So here's the energy diagram. A typical SN1 normally only has 3 bumps. This one has 4. 1, 2, 3, 4. And the reason that it has 4 is it's got this bonus bump right there because of the carbocation shift, which will sometimes occur when you have secondary carbocations. How is this reaction related to the DUI table? Well, it's the reverse of the reaction of a secondary alcohol with hydrobromic acid. In the DUI table, if you knew that you were mixing a secondary alcohol with hydrobromic acid, you would identify the mechanism as SN1. The asterisk tells me that the SN1 has the potential for a shift. So just like the DUI table, the solvolysis reaction utilizes the same mechanism. It just pushes it in a reverse order. So in general, the solvolysis mechanisms, especially when the solvent is water, are the same as the DUI mechanisms for the, well, I'll leave it at that. So if it's a secondary alcohol, we expect it to go SN1 with a shift. If it's a secondary alkyl halide in solvolysis, we still expect it to go SN1 with a shift. That's what this question is trying to get at right there. This last question right here probably isn't that helpful if you haven't done this in the laboratory. So let me explain the laboratory setup a little bit. In the laboratory, we run this reaction right here, only we use terpetal chloride. So students walk into the laboratory and they get a bottle of terpetal chloride, which is a liquid at room temperature, and they pipette out a known mass of terpetal chloride, and then they add that terpetal chloride directly to a mixture of water and isopropyl alcohol. It's both water and isopropyl alcohol because while water is the reactant that we care about, the terpetal chloride is not soluble in the water, so the isopropyl alcohol has to be there to help things out. And the students typically set up about 100 milliliters or so of that reaction. There's a lot of chemicals reacting, and what we're actually trying to do in the reaction is calculate the relative rate of the reaction. And it's a kind of a neat lab because it asks you to go back and think about the math that you did in Chemistry 106, only we just gave you the equation and we wave our hands at the math and we kind of expect you to have forgotten it. But you do, at the end of it, determine the rate constant, which was kind of cool. From an experimental perspective, you talked about it in the classroom. Now you get to see it in an actual laboratory experience. The problem is that this reaction, where the chloride falls off to form a carbocation, and then water captures it and water gets deprotonated, this is the exact chemical reaction with the exact mechanism we do in the laboratory. It's actually really fast. And so one of the ways to slow down the reaction is to add acetone, and we call that quenching the reaction. So it says this reaction can be quenched by adding acetone. Now, I just showed you on ChemDraw an example of terpetal chloride, but all alkyl halide solvolysis reactions can be quenched by adding in acetone. And what happens is, this is what happens in that first step. So all I did was copy and paste the mechanism from the first step, okay, and just copy and paste it down here. But now I'm trying to explain why it is that the bromide is falling off. And I think I showed this diagram before, but the concept is that the halogen just doesn't really just pop off. Like our pets' heads don't just fall off. Something has to go in there. It's a reference to a show called Dumb and Dumber. If you haven't seen it, I can't recommend it. Anyway, the bromide ion can pop off here only because there's a bunch of water molecules that are making strong, almost hydrogen bond interactions. This is oxygen bound to a hydrogen, so that's half of your hydrogen bond sandwich. But this, in order to make a full hydrogen bond, needs to be a nitrogen, oxygen, or fluorine. It's not, it's a bromine. So it's not quite a hydrogen bond, but it's still pretty strong. And what happens in this step is that enough waters, and actually the water is really small in comparison to the bromine, so you can actually end up with 20 or 30 water molecules that are all kind of wrapped around this thing and ripping that bromide off. Well, what happens when you add acetone? The structure of acetone looks like this. We have an oxygen right here. And then these are just methyl groups down here, and this is a carbon right here. And so the problem with acetone is it does not have any potential hydrogen bonds. This carbon carries a positive charge, but the bromide can't stick to it very well because it's shielded by these methyl groups. And these methyl groups just don't have that same strength of positive charge attraction. So that means that this acetone right here, when you add that to the solution, it starts to take the place of these water molecules. And without water there to kind of twist off the bromide, kind of ratchets it, but just kind of pops it off. You put acetone in there, and acetone's not strong enough to do it, and the reaction slows way down. And so when we're running this experiment in the laboratory, and the students are trying to see how fast it is that this reaction is occurring, it's occurring many thousands of times per second. And so if you want to slow that down, so what you do is you want to take a time frame at 15 minutes, how much chemistry had occurred, but it takes you 5 minutes or so to analyze the chemicals, so you need them to stop reacting while you're analyzing them. So what you do is you just dump a bunch of acetone in there. The acetone prevents the water from twisting the chloride off of the rest of the molecule and stops the chemistry from occurring. So the question asks, this reaction will be quenched by adding acetone. Solvents play an important role in the chemistry. The addition of acetone reduces the number of waters that are available to pry off the bromide ion in the rate determining step. And that's a big deal, because if the solvent isn't involved in the rate determining step, then it doesn't really matter what the solvent is in terms of the rate of the reaction. It's only because, in this case, the water solvent is involved in the rate determining step that you can actually change the rate of the overall reaction just by switching out the solvent. One of the lies that we tell you in general chemistry is that a reaction is affected by the concentration of the players, of the chemicals, and not a lot else. But there's a lot of things that affect the rate of the reaction. A solvent's definitely one of them, and that's kind of the topic of today's lesson. So I used this example right here as a way of kind of introducing you to the solvolysis reaction. It was also a nice review of the solubility of water, alcohols, and alkyl halides from the previous chapter. We got the drawn energy diagram, but also we got to think about kind of what effect does a solvent really have. And so that's the introduction for today's class. All right, this table addresses a half-truth that I've implied to you. And what I've said in the past would lead you to believe that a chemical reaction will either go SN1 or it will go SN2. And the answer is it's a spectrum. And so what I mean by that is you consider just a single drop of water, a raindrop falling from the sky. That drop of water has probably in the ballpark of 10 to the 19th or 10 to the 20th individual molecules of water inside of a drop that small. And the reason I point this out is if you think about a typical reaction that a chemist would run in a laboratory using some number of milliliters of the reactant, you're talking about 10 to the 19th or 10 to the 20th molecules at almost a bare minimum. Very rare for a chemist to run a chemical reaction that doesn't have 10 to the 20th molecules of reactant. And 10 to the 20th is, what is that, 100 pentillion? It's a ridiculously large number. So when we say that a chemical reaction goes SN1, what we really mean is that the majority of those hundreds of pentillions of molecules are following an SN1 pathway. Some of them will go SN2, and we just kind of ignore those. And the same thing is if it goes SN2, then sometimes it'll go SN1. And things like primary carbocations, which I've said you should never draw in your mechanism, actually will occur in very, very small amounts inside of a large container. And so the reason you don't show those is because they represent just a very minor occurrence. You want, as a chemist, to be able to predict what's the most likely thing that's going to occur. So the reason that this table kind of addresses that spectrum is when you have, let's say, for example, a substrate. This refers to my alkyl halide, for example. If I have an alkyl halide and the alkyl halide is tertiary, then it is much more likely to be SN1 than if that alkyl halide is primary. When an alkyl halide is secondary, then it's not quite so clear-cut if it'll go SN1 or SN2. It's kind of now in the middle ground of the spectrum. And so we can actually kind of manipulate the spectrum by affecting these two things right here. And what we'll find is that for an alkyl halide, that's the substrate right here. So you guys should make a note here that this is most likely going to be an alkyl halide. There's some other substrates we'll look at later on. Just that's your organic compound. If it's tertiary, it's much more likely to be SN1. And if it's primary, then it's much more likely to be SN2. And so if it goes SN1, but it happens to go secondary, if it's a secondary compound that goes SN1, it'll go much slower. So we want to kind of describe what's going on right here. So in words, a more substituted carbon favors SN1 by stabilizing the carbocation. So if it's a tertiary, then we expect it to go SN1 because we can stabilize the carbocation intermediate. Instead, if you have the more substituted carbon also inhibits SN2 because it's sterically cluttered, which hopefully is a concept that you remember from before, that in order for the nucleophile to come in, which is the rate determining step of an SN2 reaction, you got to be able to get into that 180-degree backside position. And the more sterically hindered the substrate, the less likely that is to occur. So a more substituted carbon favors SN1 by stabilizing the carbocation. It also inhibits SN2 because it's sterically hindered. And so then the opposite is true. If it's a methyl group, then you can't stabilize the carbocation, so it's unlikely to go SN1. And it's also more likely to go SN2 because the methyl group doesn't have any steric hindrance, so it's easier for the nucleophile to hit it. So this statement right here, while I only addressed really what happens with SN1 and how SN2 is unfavored, if you say the reverse of that, you'll explain why SN2 is favored by less substituted carbons. Okay, the next factor is the nucleophile. So let's kind of take a gander at the nucleophiles we've seen so far today. There's only been one, water. Water is the only nucleophile that we've looked at today. What we find is that if your nucleophile is very strong, then you have a tendency for the reaction to go SN2. The reason for this is in the rate determining step of an SN2 reaction, the nucleophile comes in at exactly the same time that the leaving group leaves. So a good, strong nucleophile can make that happen. A weak or poor nucleophile is not going to attack things until it's motivated by the presence of a carbocation. Water is actually a fairly weak nucleophile. It does not contain a net negative charge. So in this particular case, the water is only going to come in and hit that carbon once the carbocation has already formed. Before the carbocation forms, water's just not a strong enough nucleophile to come in there and push the bromide off. So a weak nucleophile tends to wait for the carbocation to form, and a carbocation is the central feature of an SN1 reaction. A strong nucleophile doesn't have to wait for any type of carbocation to form, so it goes right to the SN2, where both the nucleophile comes in and the leaving group takes off in the same step. Now, while water is a weak nucleophile, it has a tendency to have high concentrations. So we're going to see a lot of reactions where water is an SN2 nucleophile, simply because water concentrations can get out of hand in a hurry. And that has to do with the molecular density of water. On kind of a drop per drop basis, water droplets pack in more total water molecules than droplets of most other substances. So if you accidentally let one drop of water fall in there, your concentration of water is actually quite a bit higher than if you had a drop of like hexane fall in or something like that. So just because of its molecular density, it's really easy for water to reach this high concentration. Low concentrations tend to favor SN1. And so if a nucleophile is weak or unavailable, meaning low concentration, then the reaction is driven by the formation of the carbocation, so you have to go SN1. If you have a high concentration, then you tend to go SN2, or if it's a very good nucleophile. These brackets right here are a shorthand way of saying concentration. So when you say a chemist put brackets around something, then we're referring to the word concentration there. The last two factors don't really shift the spectrum. So there's a spectrum. Chemicals will be either on the SN1 side of the spectrum or on the SN2 side of the spectrum or somewhere in the middle. And so these first two factors right here can actually shift that spectrum, and you can make it more likely to be SN1 or more likely to be SN2 depending on what you do with the substrate or the nucleophile. The solvent can't shift the spectrum. It just penalizes you or rewards you depending on what type of mechanism you're running. And there's two basic types of solvents that we focus on. One is called polar protic and one is called polar aprotic. The polar is shared in common with both of these types of solvents. Both of them have to be polar, so let's talk about why that is. In order for an SN1 or an SN2 reaction to occur, think about that letter N in SN1 and SN2. That stands for a nucleophile. Most of your nucleophiles are ions, or in the case of water, a very polar molecule. And so your solvent needs to be able to dissolve the nucleophile. So in order to dissolve a very polar or even extremely polar ionic nucleophile, your solvents generally are going to be polar. So then we focus not on whether or not they're polar or not, because they're all going to be polar if it works. We're going to focus on whether or not your solvents are protic or not. Protic means that it can make hydrogen bonds. And more importantly, protic means it has the hydrogen that's required to make hydrogen bonds. Aprotic means that it does not have the hydrogen that's required to make hydrogen bonds. Let's go back to acetone. Acetone can make hydrogen bonds, but it does not have a hydrogen that can make hydrogen bonds. Acetone can only make hydrogen bonds if something else brings that hydrogen to the table, like a water molecule or something. So if you think about water right here in acetone, this is, let's circle it. This is a good-looking hydrogen bond right here. And you've got a hydrogen in the middle, surrounded by oxygens, nitrogens, or fluorines on either side. And if I try to take a water molecule and make a hydrogen bond on the other side of this one, turn this right here, that is not a good hydrogen bond. And we have, and a reason why it's not a good hydrogen bond is that your hydrogen bond needs to have a hydrogen in the middle and an oxygen, nitrogen, or fluorine on both sides. So this is not a hydrogen bond. So acetone can accept hydrogen bonds if somebody else brings the hydrogen to the table, but it cannot make hydrogen bonds on its own. And so that makes acetone a polar aprotic solvent. Water, on the other hand, is a polar protic solvent. Okay? So this cannot donate hydrogens into a hydrogen bond. So even though it has hydrogens, and even though it can make hydrogen bonds over here, it cannot take its own hydrogens to make hydrogen bonds. So as a solvent, it is called aprotic. This water solvent right here is protic. And it's protic because it can donate a hydrogen directly into a hydrogen bond. Protic solvents, like water and alcohols. Okay? If I just change this over here to methanol, then this methanol still is a protic solvent because this hydrogen right here can participate in hydrogen bond interactions. So this protic solvent right here messes up SN2 reactions. So let's consider a fairly simple SN2 reaction. Here I have a chloride ion, and it's going to come over here and push off a bromide from a terbutyl bromide or some other type of organic compound. Now normally we wouldn't see an SN2 reaction on a tertiary alkyl halide So let's make this the hydrogen. Now we have a secondary alkyl halide, and SN2 is actually what we expect to occur for a chloride ion pushing off a bromide ion. So I have the nucleophile coming in, and the bromide needs to fall off as a leaving group. Because it's an SN2 reaction, there's going to be an inversion of stereochemistry. So let's make this a stereocenter. We'll have the ethyl group coming out at you, the methyl group going away from you. And if you remember, whenever you see an SN2 reaction, we tend to see that inversion of stereochemistry. So the new chlorine is going to be in the same plane, flat, relative to the screen that the bromine is, and then the umbrella kind of flips around. So we'll have methyl group is still going away from me, but now it's tilted back the opposite direction, and we have an ethyl group. Let's make sure that I drew this correctly in ChemDraw. I'm going to go ahead and put the stereochemical labels on these ones, and we should see an inversion of the stereocenter. Good. Okay. Didn't screw that one up. Okay. So this is a standard SN2 reaction. It has one step. There's just one arrow right here showing that everything happens. This is a concerted reaction. This one step is my rate determining step. Now, this reaction occurs inside of a solvent. The solvent has to be able to dissolve this, this is 2-bromobutane, S2-bromobutane. So we need something that can dissolve that S2-bromobutane. We also need something that is capable of dissolving chloride ions. And you can't just buy a box of ions. They have to have a counter ion associated with them. So normally what you'll do is you'll go over and get some reagent grade sodium chloride, which is a higher purity than table salt, but probably not by much. And that reagent grade sodium chloride is going to be added to your reaction container, and it's not going to dissolve in just straight S2-bromobutane. I don't believe that this is polar enough to kind of tug apart the ionic lattice of sodium chloride. So you're going to need some type of solvent that will allow you to kind of tug this apart while also dissolving that. And water won't work. And we talked about this before, that two problems with water. One is if you put water in there, then it's not going to be able to dissolve an alkyl bromide. And two, if you put water in there and somehow it does dissolve, then the water is going to be your dominant nucleophile, and you're going to end up with water doing all your chemistry and sodium chloride not doing your chemistry. So let's use acetone. Let's go back and think about that structure that I drew before of acetone and ask if acetone is capable of dissolving this chemical reaction. So I'll put a methyl group here, a methyl group here, and an oxygen right there. And the answer is yes, you could absolutely run this reaction in acetone. And be a pretty good solvent for this one. The oxygen is a strong partial negative charge up here because it pulls all of the electron density on top of itself. The carbon is a strong partial positive charge because it's directly underneath the oxygen. And so that's positive, negative is actually going to tease apart the sodium chloride, and you're going to end up with these chloride ions kind of loosely associated with the body of the acetone. It's kind of like this. There'll be a bunch of these acetone molecules. The carbon with a positive charge will kind of be stacked around this, but they're going to hold that chloride in solution, but they're not going to hold it very tightly. Another common solvent that's often used in the organic chemistry laboratory is acetic acid. And so this is the structure of acetic acid, and just to illustrate the problem with acetic acid in this reaction is I'm going to go ahead and draw out that bond. This right here is a polar solvent. It's definitely polar because the oxygen contains a partial negative and the carbon below the oxygen contains a partial positive, but it's aprotic. And the reason it's aprotic is because none of the hydrogens out here on these methyl groups are connected to nitrogens, oxygens, or fluorines. This, on the other hand, acetic acid, is a polar protic solvent. So this polar protic solvent is very good at dissolving both 2-bromobutane. You can put a lot of 2-bromobutane into liquid acetic acid. Liquid acetic acid smells really bad. And maybe you like the smell of vinegar, and that's about 3% acetic acid. Concentrated acetic acid is about 60% acetic acid, and it just is strong. It takes some getting used to. The problem, though, is that that hydrogen out there on the end of the acetic acid is going to bind the chloride ion a little too tightly. In fact, it's going to gum up the chloride ion. I call this gumming up the nucleophile, meaning that this acetic acid, multiple molecules of acetic acid solvent, are going to situate themselves around the negatively charged chloride ion and kind of gum it up. And it actually prevents and slows down the chloride ion from going in here and plugging into that carbon in the rate determining step. So a polar protic solvent will slow down an SN2 reaction. And that's what this table is trying to show you right here, that the solvent that you want for an SN2 reaction is a polar aprotic solvent, because a polar protic solvent, like acetic acid, tends to gum up your nucleophile. It solvates the nucleophile too well. This chloride ion is just too happy in solution and is unlikely to come over here and push into that carbon. That does not mean that the reaction will necessarily start to go SN1. It just means that it goes really, really slow. So a polar protic solvent is a bad idea. A polar aprotic solvent is able to dissolve sodium chloride, but the chloride ion is not stabilized as well, so it holds it kind of hot potato-ish. Okay, so while the acetone will dissolve the chloride ion, it dissolves it poorly, which is exactly what you want. You want this chloride ion to be able to leave the solvent and come over here and plug into that electrophilic carbon without any problems. So then you would ask, well, what about an SN1 reaction? So hopefully I was able to convince you why it is that a polar protic solvent is bad for an SN2 reaction, but a polar protic solvent is not necessarily bad for an SN1 reaction. It doesn't have to do with the proticity, it's about the polarity. So let me explain what I mean by that. This is an SN1 reaction right here. You have a tertiary alkyl chloride. It undergoes a solvolysis reaction, which is classic SN1, and this rate determining step, the chloride ion falls off and forms the carbocation. And the rate determining step is all that I care about. So I'm going to get rid of everything else here and just focus in on that rate determining step. And that's what I look at right here. That's all I care about. In that rate determining step, you actually have a transition state. So I'm going to spread these out just a little bit. The energy diagram for this tells me that the starting material starts off at some inherent energy state. It goes uphill in energy until it gets to the transition state, and then it drops down to the carbocation. The carbocation is higher in energy than not a carbocation, always, well, almost always. And so we expect this to be an endothermic step. This is a late transition state. But what does that transition state look like? Well, I think I drew it before. Yeah, but I drew it for bromine. So let's drag this up. That transition state, that highest energy state, looks like this. Okay? What's happening at the top of the hump is this right here. We typically don't bother to show transition states in our reaction mechanisms because they're kind of assumed. If the chloride falls off, then sure, at some point that bond got really stretchy, the chloride almost became a full negative charge, and the carbocation is starting to develop. What I want you to notice is that during the course of this chemical reaction, you go from a starting material that has no charge to a product that has a positive charge, and there's also going to be a chloride ion in there. So you can have both of these right here. Let's go ahead and draw that chloride ion. The solvent has to be welcoming to charged species. And what I've hopefully said enough times that you remember is that organic solvents really hate charged species. They have a hard time solvating them. And so the solvents that work best for these types of reactions are those that are best at dealing with positive and negatively charged substances. And it just so happens that the solvents that tend to be best at stabilizing positive and negative charges are those that are the most polar and happen to generally be protic. So a protic solvent is generally more polar. So an SN1 reaction doesn't necessarily care that the solvent is protic, it cares that the solvent is polar. So I should change this right here. The SN1 just wants the most polar solvent possible. That looks ugly. Most polar solvent. And an SN2 is the one that's picky about the proticity. So how do you know if a solvent is the most polar or not? Well, we experimentally determine that for you. And so this is question 3 right here, where if you read the question, for each of the following reactions, predict whether you would use formic acid or dimethyl sulfoxide as your solvent, and explain your selection in each case. And this little epsilon right there, followed by that number, is a measurement of the polarity of the solvent. So formic acid has a higher value and is therefore a more polar solvent than dimethyl sulfoxide. And we would want to use formic acid for every possible SN1 reaction, and to choose whether or not we want to use formic acid or dimethyl sulfoxide in an SN2 reaction depends on whether or not the solvent is protic. So going back to the table, when the reaction is SN1, I just want to pick the most polar solvent possible. In this very simple example here, where I have given you 2 different solvents and told you the numerical value of their polarity, you would know that the higher polarity value should be applied to SN1 reactions every time. Whether or not I choose to use the polarity values to determine if it's SN2, well, don't. With SN2 reactions, you have to know the Lewis structure, and you have to determine if they're protic or not. So let's draw the Lewis structure for both formic acid and dimethyl sulfoxide. Formic acid is a carbonyl group connected on one side to an OH group and connected on the other side to a hydrogen. I just decided to do this off camera, but here's formic acid right here. Definitely a protic solvent. This hydrogen can be donated into a hydrogen bond. Dimethyl sulfoxide is the sulfur equivalent of acetone, and it will do all the same solvation chemistry that acetone does, just does it a little bit better because the bond between the sulfur and the oxygen happens to be more polar than the bond between the carbon and the oxygen. And that is something I can say based on experimental evidence and doesn't really match up as well with electronegativity values. But this is a really, really useful non-polar solvent. And in fact, my dad, who's a veterinarian, he'll use DMSO, is what it's called, dimethyl sulfoxide. Its common abbreviation is DMSO. And he uses DMSO, he'll dissolve aspirin inside of DMSO and then put it directly, that kind of mixture of dissolved aspirin. He'll put it on a horse's leg, and the DMSO will actually cart the aspirin directly through the fatty skin tissue onto the site of pain for the horse. Humans can do the same thing, but dimethyl sulfoxide smells awful, and if you get any inside of your system, it tends to leave kind of the taste of rotten eggs in your mouth, and then that taste affects everything you eat. So I don't know that horses care as much, at least they haven't told us that they care. But if I were a human, I would not let somebody put aspirin on my leg using DMSO. I would rather have some leg pain that aspirin could do something about. Anyway, so these right here, protic solvent right here, aprotic. So for an SN1 reaction, you choose whichever one is more polar. For an SN2 reaction, I want to avoid formic acid because it's a protic solvent. So if we go back to the question, I went ahead and made a note here that this is a tertiary alkyl halide. This is a solvolysis reaction. So solvolysis of a tertiary alkyl halide is typically SN1, and SN1 reactions are favored by the most polar solvent, which in this case is formic acid, because it has a higher polarity value at 58 versus 48.9. This is a primary alkyl halide. We're going to learn later on that, well, hopefully you know that you can't make a carbocation with a primary alkyl halide, so it's going to be exclusively SN2 to avoid the primary carbocation formation. SN2 reactions, so it prefers an aprotic solvent, which means that I want to use DMSO. DMSO is my aprotic solvent, and I do not care about these polarity values. They are meaningless to me in an SN2 reaction. I just care about the Lewis structures. Whereas when it's an SN1 reaction, I don't care about the Lewis structures, I just look at these numerical values. So this last one right here, if you draw the structure out, this is also a tertiary alkyl halide. I'm doing a solvolysis reaction, just not with water. This happens to be methanol. So this is a methanolysis reaction, but it's SN1. And so SN1 reactions prefer the most polar solvent, which would be the formic acid. Okay, let's go back up and fill in some definitions right here. Solvent effects. So solvents can stabilize or destabilize the transition states. And so for an SN1 reaction, you typically build up a lot of charge in the transition state, and therefore you want a more polar solvent. For an SN2 reaction, you need the nucleophile to attack the electrophile during the rate determining step. And so you want to avoid a solvent that sticks too tightly or gums up your nucleophile. And so you avoid a protic solvent. You might ask the question, well, what happens if I'm asked to choose between two solvents? Both of them are aprotic. And so by avoiding a protic solvent, you choose an aprotic solvent. So let's say I have two different aprotic solvents. They both will work just fine for SN2. How do I decide which of those would be a better solvent? And the answer is, I don't know. So I won't ask you that. So in the reactions where I ask you which solvent would be better, it's one of them is going to be polar, one of them is going to be, one of them is going to be protic, and one of them is going to be aprotic. And they will have differences in their polarity values. And so you're just using these criteria that we've established right here to decide first if the reaction is SN1 or if it's SN2. If it's SN1, look for the most polar solvent, and if it's SN2, pick the solvent that is aprotic, that is not protic. The dielectric constant is an actual measurement. It's a laboratory experimental, let's call that measurement of the polarity, i.e. we use the epsilon symbol is equal to some numerical value, like 58. And let's see if symbol font will work for me on this one. Yep, there we go. Epsilon is equal to 58. That's typically how we report the dielectric constant. The last concept that we need to dig into now is this idea of substitution versus elimination. And that's what the last example that I'm going to walk you through will kind of help you understand of what is the difference between substitution and when do you see elimination and why does it occur sometimes and not the other times. Before I move on, I think I didn't kind of walk you through these words that I have written here. The solvent, so we look here at this table. And for an SN1 versus an SN2 reaction, the solvent, and I've said this now a couple of times, but the solvent can preferentially increase the rate of an SN1 reaction if you go with the maximum polar solvent, or it can make an SN2 reaction faster if you choose the aprotic solvent, but you can't add like a high polar solvent to what would normally be an SN2 reaction and expect very high polarity to switch the mechanism. Solvents aren't powerful enough to typically switch your mechanisms in the examples that I'm going to give you. So we just try to match up the solvent with the mechanism that we expect from these top two factors here. If it's tertiary, it's going to go SN1. If it's primary methyl, it's going to go SN2. And if it's secondary, then we have to split hairs over what's going on with the nucleophile. And I'll give you some tables that address that later on. Finally, the last thing is in terms of leaving group ability, and we've hopefully talked about this before, and this isn't new to you.
when a leaving group falls off, the solvent has to catch it. And in my mind, I hear the solvent groaning when you try to dump one of these negative charges into an organic solvent. It's like, no. And so if the leaving group is a very high concentration of negative charge, like a teeny tiny fluoride ion with a -1 charge, that's gonna dive bomb your solvent. The solvent's really gonna struggle to deal with such a concentrated negative charge. The tosylates, on the other hand, these oxygens that are next to a sulfonyl group and often has resonance delocalization, or a really well spread out negative charge, and the solvent can wrap an army around those things, so it makes them a very, very good leaving group. In fact, we can put a couple more of these in here. I've seen the data, and these tosylates are really impressive. Maybe that's how they're 2 greater than symbols. Of the halogens, the iodide is the biggest one, so it's going to be the best leaving group. Solvents prefer to solvate negative charges that are distributed over the largest possible area, and that makes them a better leaving group when the solvent is okay with them. Okay, let's now look at the reaction of sodium hydroxide with 2-bromopropane. And let's go back to our table here, this one. 2-bromopropane is a secondary alkyl halide. And so that means that the fact that it's secondary doesn't really distinguish very clearly between whether or not it's SN1 or it's SN2. Sodium hydroxide is a strong nucleophile. And so we expect that a strong nucleophile like sodium hydroxide, and the reason it's strong is because it carries a negative charge. So that generally makes it a pretty good nucleophile. And that negative charge is isolated to a single oxygen atom. Can't go anywhere else. There's no resonance. And it's a small atom, so it's a pretty good nucleophile. And so we expect that to go SN2. So what I have shown here in red is the black is the starting material, and in red I have shown you what that SN2 mechanism looks like. This hydroxide right here will come, and its electrons will find the gap between the 2 methyl groups and do a backside attack on the electrophilic carbon 180 degrees away from the bromide leaving group. And this isn't a chiral center, but I still kind of showed that inversion process where it flips that umbrella inside out. And the hydroxide is now connected as an alcohol to that electrophilic carbon. This is the SN2 pathway. The problem with hydroxide, and what makes it unique and problematic, is that it's also a good base. It's not the strongest base that we'll ever see, but it is a strong enough base that if, when threading the needle right here between these 2 methyl groups, if it happens to bump into any one of these 6 hydrogens, the hydroxide will simply just grab that hydrogen, take it and leave, and the hydrogen's electrons will fold down to make a double bond, and then that pushes off the bromide. This is called an elimination mechanism. Substitution, S, and elimination, E, are the 2 major mechanistic pathways that we see in organic chemistry. And in fact, you'll recognize them if you go on to take biochemistry. There's a whole bunch of biochemical reactions that essentially involve either substitution or elimination. Biochemistry doesn't want carbocations, doesn't want these very high energy intermediates. So almost all reactions in biochemistry are either SN2 or E2, and definitely not SN1 or E1. Organic chemists, we don't care. We're not trying to preserve the living integrity of our reaction container like cells have to. So if we drop a carbocation in the middle of our reaction container, we're not worried about that just breaking through the walls of the flask. But if you drop a carbocation in the middle of a biological system, you just dropped a hand grenade in that cell. So they don't want carbocations. So they'll go SN2 and E2. Organic chemists will do SN1 and E1 as well. But this is right here a strong nucleophile. So it does not wait for a carbocation to form, and it's a strong enough base that it just rips that hydrogen off, and we end up with this E2 pathway. So the question you should ask is now, well, which of these 2 pathways is most likely? So in question number 4, I've now shown you the substitution mechanism in red, and I've shown you the elimination mechanism right here in magenta. I think that's what that's called. The pathway that is chosen depends on the energetic diagram. So here I have that reaction coordinate that we've seen before. Only now, if you're this molecule and you're in this high mountain valley, and your goal is to get as low as possible, that's a spontaneous process. The question is, do you climb over a shorter mountain to get down to the lower valley, or do you climb over a higher mountain to get down to the lower valley? And the answer is, the majority of the time, molecules will choose this shorter pathway. And so kind of the tidbit to memorize here is, in the case of secondary alkyl halides, in the presence of a strong base like hydroxide, elimination is typically favored over substitution. But so far, all you need to recognize is that both of those are happening simultaneously. The majority of the molecules are going to follow this E2 pathway. Some of the molecules are going to follow this SN2 pathway. And so you're going to have to clean up this reaction when you're done, because your final reaction container will have some of this alcohol and some of this alkene. This alkene would actually be a gas at room temperature, so that would be an easy way to separate it. You set up a balloon gas collection flask, and then you have a liquid collection flask, and you go ahead and it purifies itself for you as the chemistry occurs. That would be a nice reaction to run. These alkenes smell awful, and I'm not sure why evolutionarily we are predisposed as humans to hate the smell of alkenes, but when you set rubber on fire, it produces a bunch of alkenes. So the smell of burnt rubber is the smell of alkenes. Some people say that wrong, and they say that alkenes smell like burned rubber, and that's what you say if you're not a good chemist. A good chemist would say that burned rubber smells like alkenes. What would happen if I clipped this methyl group off right here and made it a primary alkyl halide? And so I drew that. So here's that same hydroxide mixed with now an ethyl bromide. So this is a primary alkyl halide. And now you think, this hydroxide on its way into the carbocation, not the carbocation, the carbon, has all this room over here. There's no methyl groups over here to kind of mess it up. And so what it means is it's actually easier for the hydroxide in the case of a primary alkyl halide to do an SN2 reaction. And it's less likely that it will do E2 chemistry. So that's what this table is trying to show you. In the case where you have, the first example we looked at was a secondary alkyl halide in the presence of hydroxide. And we saw that the E2 route was energetically easier than the SN2 route. And the problem with the SN2 route is that that hydroxide has to slip in between those two methyl groups, make it all the way to that carbon without bumping into any of the hydrogens. And given the kind of the inherent molecular vibrations or wiggliness of these compounds, that's just a low probability event. You're much more likely, in the case of a secondary alkyl halide, to see elimination chemistry occur. So this is going to go E2 more often than it goes SN2. It's still going to see some of both, but you expect E2 to be your major product, and the major product is the thing we care about the most. That's where you get all your points. Okay. If we now have a primary alkyl halide, then that whole side is open, and the hydroxide really doesn't struggle as much to make it into the carbon. And so what we see is the SN2 pathway versus the similar E2 pathway for a primary alkyl halide. The SN2 is a lower activation barrier, so we expect this to be the kinetically favored process. This just happens faster. When everybody's at the valley and they kick everybody out of the valley, they're going to go over here. It's just a smaller mountain to climb. So for a primary or methyl, we expect SN2 to be the dominant mechanism and E2 to only be a secondary mechanism. Well, now let's go the other direction. Instead of clipping off a methyl group, let's add in a third methyl group. So that's the example I have right here. Things got cluttered pretty quickly, and you'll see that that presents a problem. If you have now a tert butyl bromide and you put hydroxide in there, it makes sense that if this hydroxide is trying to make it to this carbon right there, that's such a low probability event that I never even bothered to draw the red arrow. It's going to pull a hydrogen off almost every time. And the energy difference between those two, I made it as exaggerated as possible, and even then I don't know that I really showed it to scale. The elimination for a tertiary alkyl halide is such an easier pathway than trying to squeeze that hydroxide past all of these gatekeepers into that carbon and get your unlikely SN2 reaction. So I didn't even, you need to kind of pencil that in if you want. The question doesn't ask for it, but I just didn't bother. It felt ridiculous to me to try to show an SN2 reaction on a tertiary alkyl halide. So this isn't even a case where the E2 is greater than the SN2. It's just E2, the end. That's all you expect to see over and over again. Now, given a trillion molecules in solution, one of them will go SN2 just to prove me wrong. Yeah, they'll do that. But when we're talking about large numbers of molecules and what we expect to be the most probable event for tertiary alkyl halides is definitely E2. Okay, so the purpose of today's lesson was to start to introduce you to three ideas. One is that we're going to need to deal with these tables right here, that alkyl halides are actually a little bit more complicated than alcohols. And with alcohols, we kind of fleshed them out where we had HCl, HBr, PBr3, and SOCl2. With alkyl halides and their related kind of overweight cousins of the tosylates, kind of these big alkyl halides, they're going to have quite complicated tables. And so we're starting off very simply with this right here. So the fate of elimination versus substitution for strong bases was one of today's topics. The similarity between solvolysis and the DUI table was another topic for today. And then also I want to introduce this idea of solvent effects, that there are protic solvents and there are aprotic solvents. SN2 reactions really care. SN1 reactions care about which solvent is more polar. Let's take a gander at your chalkboard problems and give you some clues. Okay. Yeah, this is a two-step process, so you're going to want to kind of stop and address what happens at the end of this first reactant, and then whatever that product is, we're going to then react it with sodium iodide. This compound right here is analogous to tosyl chloride. And so you can just go back and check your notes on what you learned about tosyl chloride. This is a compound that is very similar to it. So you'll just draw a name of the product and then show the full mechanism for everything that's going on there. And that's a good chalkboard problem. There's two parts to that. Okay, let's make sure we got the last of the definitions. Oh, substitution versus elimination. So for alkyl halides specifically, strong base nucleophiles like hydroxide will see a competition between SN2 and E2. Primary alkyl halides favor SN2, secondary alkyl halides favor E2, and tertiary alkyl halides overwhelmingly, or essentially always go E2, equal E2. Let's call it that. Let's see if spell check will help me out right here. Okay, I'll put this in bold and we'll call that a wrap. This is a very information dense topic today. There's just a lot of stuff and it was very technical. And so make sure that you've taken careful notes. If you need to, go back and kind of review what your notes say so that they're meaningful to you. And a good idea would be for you to share your lessons with another member of the class so that you can kind of compare notes to see if maybe there's something else that they picked up that you didn't.